previous video showed that the reciprocal of the gamma function could be factored in this form. And now we're going to use that to prove some of the fundamental identities of the gamma function. So first of all, it'll be more convenient to take the reciprocal. So it's 1 over z e to the minus gamma z times the product of, well, 1 plus z over n inverse times e to the z over n. Okay, so the first identity we'll prove is the reflection formula for gamma of z times gamma of 1 minus z. So we'll just apply this factorization and see what happens. Okay, so what do we end up with? We get 1 over z times 1 minus z times, okay, e to the minus gamma z, e to the minus gamma 1 minus z. Those multiply together to give just e to the minus gamma. And now we have a product of 1 plus z over n inverse, 1 plus 1 minus z over n inverse. And now z over n and 1 minus z over n add to 1 over n. So this becomes just e to the 1 over n. Okay, now let's see what this gives us. Okay, so we have, well, we can write this as n over n plus z times n over n plus 1 minus z times e to the 1 over n. Now if we look at the partial products of that big mess, what will we end up with? Well, in the numerator we'll have n factorial squared. Okay, that's a little bit scary, but it's not so bad. And then we'll have 1 plus z, 2 plus z, all the way up to n plus z. And then we'll also have 2 minus z, 3 minus z, and so on, up to n plus 1 minus z. And then for the e to the 1 over n, that gives us e to the nth harmonic number. Okay. So how does that simplify? Well, we can write the fraction in a way that makes it look like Euler's sign product. So we'll write it as 1 plus z over 1, 1 plus z over 2, all the way up to 1 plus z over n. And then we'll have 1 minus z over 2, all the way up to 1 minus z over n plus 1. Okay, that requires dividing by 1 copy of n factorial for the plus signs, and then n plus 1 factorial for the minus signs. So we actually have 1 over n plus 1 here, and then e to the hn. Okay, now remember, the harmonic numbers behave like log n plus the Euler-Mascheroni constant. So when we exponentiate, the 1 over n plus 1 cancels with the log n in the exponent here, and the e to the minus gamma goes away from the gamma in the exponent. Okay, so altogether, what we end up with is exactly 1 over the product, well, z times the product of 1 minus z over n over all integers other than 0. Okay, but that doesn't quite make sense. It doesn't converge. So again, what we do is we pair up the positive and negative integers. So we get this. Okay, and now this was exactly Euler's formula for the sine function, except where we've scaled everything by a factor of pi. Okay, so what we end up with is sine pi z in the denominator, but then that gives us an extra factor of pi out front, so we would end up with this. So to fix that, we put a pi up top. Okay, so finally this shows that gamma of z times gamma of 1 minus z is pi over sine pi z. Okay, and then we can use this to find gamma of 1/2 because we let z be 1/2, and we get gamma of 1/2 squared is pi, so we end up with gamma of 1/2 equals the square root of pi, which is the Gaussian integral, just with a slight substitution. Now we can also use the product formula for the gamma function to rewrite gamma of z times gamma of z plus 1/2. Okay, so if you think about this function, the gamma z factor has poles at 0, -1, -2, and so on. And then the gamma z plus 1/2 has poles at -1/2, -3/2, -5/2, and so on. Okay, so altogether, when you multiply them, you get a function whose poles are at every non-positive half integer. Okay, that's kind of a mouthful. But what that suggests is that it should be related to gamma of 2z. That's another function with the same poles. Now these functions aren't exactly the same, but they're pretty close. So let's say you have some function f of z that makes this an actual equation. Okay, so we can say f of z equals gamma of z times gamma of z plus 1/2 all over gamma of 2z. Now, if we want to guess what that function is, we can use the functional equation for the gamma function. So f of z plus 1 will be gamma of z plus 1, that's z times gamma of z. And then gamma of z plus 3/2, that's z plus 1/2, gamma of z plus 1/2. Okay, now gamma of 2z plus 2, we have to go back a little bit, 2 spaces, to get 2z times 2z plus 1. Okay, so now that's almost f of z, except we've multiplied by 1/4. Okay, so if f is a nice function, which it should be, then it should be exponential, and the base should be 1/4, because each time you increase z by 1, you multiply by 1/4. Okay, so if we were to guess what f should be, it should be some constant times 1 over 4 to the z. So I'll just write that as 2 to the minus 2z. And remember, this was gamma of z, gamma z plus 1/2, all over gamma of 2z. Okay, well, now the last bit is easy. Figuring out this constant requires just plugging in a single value of z. So let's just plug in z equals 1/2. We get c over 2 equals gamma of 1/2 is square root pi. Gamma of 1 is 1. Gamma of 1 is 1. Okay, so c equals 2 square root pi. All right, so that leads to this identity, which says that gamma of z, gamma z plus 1/2 equals square root of pi times 2 to the 1 minus 2z gamma of 2z. And we can get similar identities with gamma of 3z, 4z, and so on, but they get more complicated each time.